thank you for making the trek all the way out to this venue. It seemed like a long way in the hot sun for me, so thank you. So I'm going to talk today about real-time analytics. And as I've been talking at lunch to folks, and I've been thinking about this particular talk in this context, and realizing that real-time analytics really is an overused and hard to pin down topic. And what I'm going to talk about here is not analytic databases, fast analytic databases, or Spark type systems. I'm going to talk about the practical patterns that I've seen as the CTO of a company with the folks who are using our database. And the pattern I'm going to present to you is one where the application is really doing the math. So it's forms of coding at the application layer. So first, how many of you have heard of Aerospike? This is my one slide about Aerospike. Great. So Aerospike is a large-scale DHT, essentially, distributed hash table from a computer science perspective. It's very, very good at row-oriented access. So if you need order one access to millions of objects in real time, that's the kind of system that we've built. It is an open source system, so we do have a version you can download. You can read all of our code. It does have this strange capability that we call hybrid memory, which is the ability to use Flash in a very native and optimized fashion. So what we do is we put the RAM, we use RAM for the indexes to the database, and we put the actual data itself, the bulk storage, in Flash. And it turns out if you do that in a clever fashion, you can build a super fast database. The system is also clustered in high availability. So you can go read the code, and if anyone wants to talk database internals, distributed systems after the talk, happy to do so. This is more about application layer. So what we used to do, what some people still do, on the front edge of their application, as they're building more and more of these applications, is to use a fairly standard operational data store, say a MySQL or a system like that, and then put a cache in front of it. If you're like me and you've been recently to the Redis website, you'll see Redis is telling you need to put some Redis in front of your Mongo. At least those ads are following me around the internet, so they're probably following you around the internet also. These two layers then become how you balance the necessary read capabilities as well as having persistent storage. So that's what we've been doing for a long time on the front edge of our application. The problem is those performance characteristics get kind of slow. MySQL is a system that is in the 5,000 to 10,000 transaction per second range, and that's if you miss cache. So you have to know the caching size, you have to build out that layer, you often have to build a consistent cache using consistent hashing, and use a hash layer, right? These are all kind of common terms, systems from that. So what we believe in is that you can actually have a database that is at hundreds of thousands to millions of transactions per second as your operational data store without a separate caching layer. So the whole point of that is that it enables you to build out much more interesting applications. I'll show you sort of the application design pattern for that on your real-time front-edge data. Now, what's important about that is I've put it small here, but that's not to minimize the importance of your actual batch analytics system. Of course you have Hadoop. Of course you have a Spark system. Of course you have a whole bunch of HBase and you have a data lake, right? Of course you have those things. You need a set of analysis, you need insights, you need machine learning, you need audience segmentation if you're doing anything in retail or on the internet or integrating with advertising, all of that stuff. But those are batch systems. At some point, you actually have web requests coming in, and those need to be satisfied now, right, in human time. An interesting part about anything that's happening in that human phase is, an important part about this is an average website often takes between 50 and 100 different web requests or sub-calls or object calls in order to build a web page. If you think about that, and you can go and look at a variety of sites. Amazon is about 100, CNN is about 130 right now. What then happens is that your 99% latency at this layer, as you're going through microservices and the various REST calls you need, becomes your average time. So instead of thinking about database average latency, you have to think about your 99% latency. That becomes your average latency when you're dealing with these kind of rich applications that are taking 100 different requests to build out an individual response to an end user. So for that reason, we'd be using caches, but the problem is you then need these really high cache hit rates. If you have a database that is capable of these kind of speeds, possibly with an integrated cache, then you get through a lot of those problems. So some people then say to me, well, Brian, rarely do you need 1 million transactions per second. I mean, 1 million is a lot, and seconds are a lot. If you go to Oracle's website, what do they talk about? Transactions per minute? Transactions per hour? And here's the basic piece of math that becomes interesting, is the number of individual portions of data you need in a analytics-based application. So this is taken from a real-world case study where it happened to be a payments gateway system. And the number of transactions per second that are flowing in North America at the very high peak times are actually about 5,000. It's about 5,000 payment requests and credit card swipes in the high seconds, in the high moments in North America. Well, that's only 5,000. So you should be able to satisfy that with one MySQL instance, right? Well, but here's the problem. If you're actually doing analytics on that front edge, you might need several thousand data points in order to do the analysis that you know as a data scientist is effective in determining, say, fraud in a payments processing system. At that point, once you need this kind of math, you end up in the millions area. So being able to support high transaction volumes, you can think about this as transactions, but these are in support of analytics cases, right? The business transaction is only one transaction. But the amount of data points you're going to need to satisfy and that is going to give you an accurate representation of fraud may be thousands in order to satisfy what you need. That is the core argument behind why many applications, transactional analytics systems need this kind of transaction volume. Now, the key that I've seen to these systems succeeding, so first of all, don't use small gray lines on your slides. Anyone will tell you that small gray lines on your slides is a really bad idea. So I do apologize. Oh, look, let me fix this. There we go. That's my son. Oh, there's one here too. Okay. So one way to think about these systems that I found is effective is instead of thinking about your transactional or front-edge analytics in terms of large queries. So instead of trying to reduce that kind of a fraud detection system, imagine that, into a SQL system where you're creating a fairly complex representation, instead, write some code. It is now easier to write in code or use a machine learning system that's going to go generate a huge number of data point requests. And then you can use whatever streaming analytics framework you want. So if you're using Spark, if you're using Storm, if you're using, I can't remember this guy, Flink. I just put him in today. This one is Heron, the great Heron talk, I think, in the next session. So whatever your team is used to is really the framework you should use. And what that means is your database can be more generic and support a greater number of these systems. So what I'm arguing for here is a system that you don't have to reduce your query into one format. You're not using a single graph database. Instead, you're doing graph-oriented single-point lookups. So the good news about single-point lookups, think key-value store or row store, is it is inherently scalable, right? Any computer scientist will tell you, well, if you just want to get one thing out of a hash table, that is a solvable problem at very high scalable speeds. The hard part is distributed indexes. So that's the pattern that I found works. Let's say, for example, you're in Storm. And in Storm, you get a message, and that message has a user ID. That's a key-value lookup. Instead of going off and doing a complicated query to a high-performance database, a NoSQL, a Snowflake, just go and get that user ID. That will be insanely scalable. Let's take the case of trying to do network analysis, fraud detection based on IP address. Well, there's only about 4 billion IP addresses in the IPv4 network. That is now a reasonable system for a database, a scalable database. You can just have one object for every IP address. And you can go and look up the recent behavior there. Perfectly reasonable, perfectly scalable. That's the kind of system that I've seen work, partially because it allows you to use the technology that is correct for your team that is doing these kinds of analytics, as opposed to trying to render it into a complex analytics framework. Oh, well, that's the failure mode of that. So this puts into words what I was just talking about. Write code, not queries. So let's go through some examples of this. Ad tech is a particularly interesting case, and it's a case that you guys would know well here out in the LA area. So what you need to do in ad tech is put together a package that understands for individual users who is going to convert at a given time, and put that mathematically online as part of usually a real-time bidding system or some kind of conversion analysis. Often involves understanding of audience metrics, and audience clustering, right? I'm sure a bunch of people here use that. Well, an audience, there's usually an audience ID, right? So you should be able to go get that one audience ID. You want to update it? Great, update it. You want to go get all of the users in an audience, get the audience ID, then get the list of user IDs, and then go get it with a batch request. That is much more scalable than trying to go out and do a query, trying to sum up all of some particular statistic on a particular audience ID, as an example. Today, right now, there's usually about 1 to 6 billion cookies tracked throughout North America. So again, that's in the reasonable size today. You can simply create an object database with that kind of scale. You're trying to work usually within the 100 millisecond range, and that's an area where you've got a fairly reasonable amount of time. You can do several network round trips. Usually the database portion of this is only a couple of milliseconds, but it does allow you to go out and do one request, do a certain amount of computation, then get a batch for a second set of requests. Oh, let me go back to one thing. So, is this analytics or not? This is an interesting question, right? Because in some sense, you're just going and getting for a particular user, trying to figure out what the probability or price is, given what the impression characteristics are. You're doing a little bit of math. Would you really call this analytics? It's probably like multiplication, right? You're taking a couple of probabilities, you're looking at a few different tracking retargeting numbers, and you've got a very simple model. And that's the question I don't really know the answer to. Is just doing a few multiplications analytics or not? I don't know, but this is an effective pattern. Let's talk about that fraud detection case for a minute. So some of the guys that I've worked with were originally trying to use these things rules engines. And those of you who have worked in fraud detection know that what happened previously was that you would usually create new rules every month or every year, which sounds kind of crazy on the internet, right? I mean, really, a year? A year later, I'm going to change the radius of motion. I'm going to look for attack vectors. I'm going to sort through my data lake. I'm going to figure out what's fraud and what's not once a year, and I'm going to load that into SQL queries that are run on a transaction basis. So today, things have to run a lot faster. The attack vectors that can occur on the internet with card not present are really much more sophisticated than something that can be tracked or retuned every month. And so in order to do that, the pattern that we've seen people move to beyond the rules engine is the ability, just like I was saying, about being able to write code that actually embodies whatever application pattern and simply store the raw behavioral data. These particular guys, we had to work with them a lot to get them out of the relational semantic. They wanted to create a single big table with every single behavioral point. That big table in their system would end up having about 40 billion, 50 billion rows to represent a month's worth of internet big data, and then they were going to do these huge queries on it. They were having problems scaling. We said, well, wait a minute. What if you just take all the IP addresses, just have a table with all of that, and have basically a little time series on each one of those? No, I need to do big queries. No, you don't. You actually really want to go look up one IP address. So to a relational guy, this is violating some of the precepts because you're starting to embed some of your business logic inside the data structure. On the other hand, it's really fast and it works. So these guys were able to really bring online some new analytics that they weren't able to do before and succeed in their business problems. Retail trading. This is a pretty interesting case. So those of you who have read Michael Lewis's Flash Boys or Daniel Patterson's Dark Pools, pretty interesting books about how trades are settled in the modern world. And in the old days, you'd go to the New York Stock Exchange. You'd say I'd have 100 shares, and there'd be some market makers and some shenanigans, but you'd get your price. And today, what we have is about 50 different trading exchanges, some of which are dark, some of which are public. And there's rules about breaking a trade into different pieces and being able to settle on the current most efficient exchange. That's kind of hard. So what these guys needed to do was not only did they need to do risk calculations, but they needed to do this exchange monitoring. So they needed to know for a given ticker symbol, which of the 50 exchanges in North America is the most efficient right now, which is to say is clearing with the lowest bid-ask ratio now, because it turns out that changes from exchange to exchange moment by moment. So they needed to know that to be able to settle properly. Second thing they needed was risk. So we all know 2008 happened, and post-2008, if you're a brokerage house, then you need to know the margin that you've got outstanding, that's essentially your loans, and you need to have a global understanding of all of the risk you've got in your portfolio. And there's calculations for that. So pre-2008, that risk was recalculated at the end of day with a big analytics system and a big SQL query. Well, we now know that that's a pretty bad idea. Being able to move to a system that can recalculate every few minutes the entire global analysis is really a much better system. Machine learning. Machine learning ends up being a very interesting application of this pattern because it's also a non-SQL, non-relational style system. I mean, in some sense, of course it is, right? So some of the guys that I talked to doing this, they have their own system. They're not using one of the standard platforms. They're not using Spark ML, H2O AI, any of that stuff, or TensorFlow. They've got their own system. And so what they've got is they've got their data set flow. They've got feature selection, sort of standard stuff. What they need is they need the information about each individual user, their user data store, but they also need a model store. In this particular case, what they were doing is audience segmentation, and it turns out they needed 50,000 different audiences, one for each ad campaign that was currently in action. So if you're doing this kind of ad store, categorization store, what you need to do is monitor the progress of each individual ad, right? And you need to know each individual model is either succeeding or failing. And since this is an online system, it is recalculating every few seconds. There's a new model, there's a new model. And then how's that model performing? What's that curve look like? I was talking to some folks at Gum this afternoon, and they said, yeah, this is really hard because models go bad. And that's exactly what happens. Models go bad. So you have to monitor them. And if you monitor them, you'll find that occasionally a model, as it's being retrained, when it goes bad, you have to roll it back. You might have to roll it back 1 model generation, 2 model generations, 5 model generations. It turns out this takes a fairly substantial toll on your database. He called them basically a pipeline stall, because as you're doing these recomputations, you're trying to push it out to your front edge compute nodes. You simply, at some point, you hit the bottleneck in the database. The database can't serve these objects into the compute nodes fast enough. And in a multi-level store, that can be a serious problem. So in order to go along with that kind of model store, and so people often use S3 for this, right? It's a nice object store, it's in Amazon. But the problem is, when you're doing online, you really don't have enough performance to do that kind of thing. In terms of the user data store that you have along with that, it's kind of like a time series problem. Because what you have is you have, for an individual piece of data, you have a restricted amount of data points that you've sampled, right? You've gone through feature selection, you know which features are accurate, but you do want to know what the capabilities are. So with these guys, they were able to store probably about 5 to 10 tera was what they found was actually acceptable for running their real-time models. So what are some of the ideas here? One of the other ones that's interesting is telco integrated routing and feature analysis. So the problem here is how many of you have cell phone plans that now have free streaming, free Netflix, that kind of thing? It turns out if you think about how that's going to be implemented, in order to do that, you're going to have to know each individual data flow, whether you have that is to a streaming site, and then you have to do traffic shaping. In order to do traffic shaping, you have to know recent amount of bandwidth and recent packets in order to know whether to delay one. That's stateful. Well, the reason routers go fast in the modern world is they're stateless. All they've got to do is take this IP address and shuffle it from interface A to interface B. The idea of doing a network call to figure out, well, does this user have this feature turned on or not? Is this Netflix? Is it another streaming site? Have they bought in? Have they not? All of that requires database lookups. So it turns out that this kind of packet flow analysis integrated with user data ends up being a very similar kind of simple analytics right on the front edge of an interesting application. So hopefully this is giving you some ideas about how to integrate the concept of analytics, not by using back-end systems, but really by integrating your back-end and front-edge systems in kind of a novel way. And that you don't necessarily have to think about, or possibly shouldn't think about, query systems, be they SQL or NoSQL, but really should try to integrate your ideas around key-value store lookups, which are really the focus in database terms, primary key lookups, where you can actually get scalability and high performance. The fact that you can integrate all of these systems with your NoSQL systems, right? There's just about everyone has connectors for Spark in terms of having RDDs and data frame integration. We don't have a Flink one, but Storm, Kafka, all of that stuff is all integrated visually. So these systems are fairly easy to put in place, but do require you to separate out your analytics, which is to say your compute, from the data layer. And that's what I've found is the effective solution to doing analytics on your transactional data on the front edge. So, questions? Sir?
Did you ever consider using Erlang or Elixir's in-memory sort of distributed storage for this?
Yeah. It's slow. So when we built this system, it's written all in C. We're very cache line and NUMA aware. The idea of using immutable data is inconsistent, in my opinion, with high performance, because you end up making lots of copies of things. And that's the easiest way to go slow. It's hard to do mutable data. It's hard to get your locking right. It's hard not to step over yourself, but it goes faster. Any other questions? Sir?
What other databases, is it exclusively Aerospike that did this, or have you tried other databases?
So databases that can work in this paradigm are ones that focus on key value. So if you were running, say, a Redis cluster, if you were using Dynamite from the Netflix guys, that's in a very similar application pattern to this. Cassandra is often used in this kind of system. Cassandra is interesting because it can be used as a column store and as a row store. But people often use Cassandra for this kind of use. There's some other row-oriented databases. I think what DynamoDB is doing is kind of interesting. It's also very similar to what Google built with Bigtable. So if you look at the precepts on Bigtable's website of how to design applications for Bigtable, it's exactly what I'm talking about. That same concept rows separate and isolated, and then being able to have really big tables, but independent rows, is really, there's a number of databases that have followed that path. And that's really what I'm talking about, is that big table pattern is a very, very effective way to get not just a fast front-edge system, but you can also build analytics on it. You just have to move those analysis into your code, which honestly is faster and easier to understand anyway. So
you asked the question, like, what is analytics? Is it just, a few multiplications potentially? What is that exactly? Is it? I don't really come from an engineering background, so I think about, well, when I'm asked for information or insights, usually there's a join involved. So you were talking about key value stores, and how is that the possibility of having to create at least one, perhaps two joins that work with this concept?
Yeah, great question. So one way to think about a join is it's two key value lookups. It's usually one to get the set of things that you need, and then you're usually joining two. That is also a key value lookup, but it's a lot of them. So the application pattern that you would use to simulate an in-database join is get your list and then do a batch request of that list. That scales. If you push that kind of request into the database and make the database do it with a relational database, most relational databases will attempt to have what's called referential integrity and give you the precise correct answer. Doing it in the application layer, you'll get a little bit of slop to that. What if one of them changed and another one didn't change, et cetera, et cetera. However, breaking it down into those individual requests, you're kind of doing what the database might do internally, externally, but it scales a lot better.
How do you guarantee latency when the data is being updated, being migrated, etc.?
So how do you deal with latency when
you get your data updated? Because I guess the front-end data in, let's say, RSpike is getting updated from an analytics data store.
Sure. So when you're using this pattern and you actually have updates coming in from your analytics system, you also have updates coming in from your front edge. Right? New behaviors are occurring at the same time. So the database in this pattern does have to deal with both reads and writes at high velocity. And there are tricks of doing that in a key value store also in terms of how you do your row-based locking. And if you've been clever when you implement one of these databases and you've properly implemented your distributed hash table, you should be able to take both reads and writes at high velocities. Cassandra, for example, is well known for high write throughput, right? It's a pretty well-balanced database in that fashion.
Do you need to do any throttling on the update side?
Well, it depends on how many nodes you have, right? This system should be scalable. I would only, these days, recommend something that clusters, right? So you either start throttling or you add more nodes. So it depends on your business.
So the hash map knows not to handle a nodes addition like in real time without degrading the read latency.
Well, the question, should you auto-scale, is a more complicated one, and ends up being a business decision. Would you rather throttle and not do some business, or would you rather pay money to scale? And that ends up being a policy. But I would argue that any system that you implement today should have enough clustering to be able to allow you to make either choice. And you'll find that, right? So Mongo clusters, Dynamite clusters as part of the Redis family, RSpike clusters, all these guys are clustered databases. Yes?
Do you have a metric comparison on your website compared to other systems?
Yeah, we have a variety of different benchmarks.
On the website or GitHub?
Yeah, on the website. Okay, so thanks a lot.